Folks, let's get started for round number 2. We're going to be talking now about sedimentary facies. Anybody remember the term facies?
Yes, facies change.
So you're reading the notes in advance. I'm not going to talk to you anymore. I'm talking about people. The last time we talked about facies was metamorphic facies, long time ago, and I'm going to refer to that shortly. But in this case, we're not talking about metamorphic facies. We're talking about sedimentary facies and the significance of what this all means. Now, here's our agenda. First thing we're going to be doing is talking about what facies are. I'm going to try to explain the importance of this. Then we're going to talk about defining characteristics of facies, how we define them, and what the ultimate significance is all about for this. And then talking about how facies ultimately link to depositional environments. All right, now again, I want you to realize, when you go to an outcrop for the first time, assume no one has ever been there before. Everything you're seeing is going to be for the first time. In fact, I think it's safe to say, even if a zillion people have gone to an outcrop, you're going to find things that no one ever saw before. You describe what you see. Ultimately, you have to have a goal to sort out what was going on when that stuff was being produced, potentially hundreds of millions of years in the past. You do it in a series of steps. It's dangerous to go in and come up with conclusions about what you're seeing ultimately unless you have a chance to think about things. That's what we're going to talk about today. Okay? All right, so let's talk about why we do all this in the first place. So with the first lecture we had earlier, we were talking about the type of information you have to observe, how you go about representing it in a graphic fashion. Why are we doing that in the first place? Ultimately, what you want to do is to determine the nature of the environment of deposition that stuff was originally deposited in. Now, you have to understand that where we live, you can go down to the beach and realize that you're standing on a beach. This is incredibly instructive if you want to learn what kind of attributes are going to be recorded in the sediment that's being deposited at that time. So you can go down to Dolphin Island Beach and pick up the quartz sand and look at it and get an idea of the sorting, the grain size, the roundness, the mineralogy. All of that makes sense because you're on a beach. But turn it around. If I were to drop you off in a helicopter in northern Montana at the edge of a stream which had an outcrop, and that outcrop was composed of quartz aeronite sand that was deposited 125 million years ago, ultimately, what you need to be able to do is to determine what kind of environment that stuff was deposited in originally. And while it might seem easy, quartz aeronite sand equals beach, think again. All that stuff we told you in Geology 111 was more or less to get you to link the materials to what you ultimately get. But quartz aeronite sandstone is the product. You can get quartz aeronite sandstones on beaches, in deltas, in the middle of the ocean, along the edge of a tidal marsh. You can get it anywhere that quartz sand happens to be deposited, which is just about anywhere there is. If your job is to find oil, or find a supply of water, or look for a Mississippi Valley type ore deposit, knowing what kind of environment you have will allow you to determine where the sand will be concentrated. That's ultimately what you've got to be able to do. So what you're looking at here now is a nice little small inset showing you some of the siliciclastic depositional environments. This could have been done from our backyard. We have tidal flats. Well, we don't have a lot of tidal flats down here, but we have lagoons, we have the beach. Well, I guess we don't have mountains either here. Well, maybe this isn't our backyard. The point is, it summarizes all sorts of different types of environments. Every one of these things, like an alluvial fan, or a braided river, or a meandering river, or an anastomosing river, is going to have different attributes associated with the sediment that's being deposited there. One of the best ways of learning sedimentology is to go to modern environments and observe. One of the most practical things a sedimentologist can do is take that experience and go to an outcrop and say, hey, you know what? This looks very much like what I saw when I was standing along the edge of an alluvial fan in California. Okay? So that's why we're doing this. The issue here is that there are literally zillions of different types of depositional environments. All right? The neat thing is that each environment does have certain attributes that collectively allow you to resolve what the overall model was. But again, think back to the beach. If all you did was to stand along one part where the water is washing over the swash zone, all you get is one picture of what that entire beach environment was like. If you turn around and put the water to your back and look away from the beach, you're going to see sand dunes. Well, maybe not along here. We don't have any sand dunes left anymore. Cursus erosional inconsistencies. But you'll find sand dunes. Those sand dunes are completely different from the swash zone you're standing on. Turn back and face the water. Well, the beach goes out to about 10 meters water depth, which for along our part of the world is like halfway to Mexico. As you get off the edge of the beach, you're going to find differences there as well. So there's a whole bunch of different environments, but each environment has a whole bunch of subdivisions that make up those depositional environments. Now, let's consider what I mean with this by looking at something that you are not familiar with. Because again, I want you to get away from the idea that you've seen it all. You haven't. There are many different types of rivers. The rivers we have where we are meandering rivers for the most part. There are also braided streams. There are also anastomosing rivers. There are actually multiples of each of these, but each one is different because they are composed of different subgroupings. This is a cross-section or block diagram. You're going to see a lot of these in this part of the course. Actually, not this part, but in the future part of the course, which is showing you a three-dimensional schematic model of what you would get if you were in a braided stream environment. By the way, the nearest braided streams that we have to where we are now are literally in Western Canada. You need to be in an area where you have topography. These things form on relatively steep slopes. You also need to be in a place where you have mountainous areas, because these things are largely composed of gravels. The best braided streams I've ever seen are in New Zealand. The second best, which I've not seen but I understand are wonderful, are in Alaska. The closest ones, as I said, are in Western Canada. Now, if you look at this block diagram in detail, you're going to see that it is showing you all the different attributes that a typical braided stream could ultimately have. And within this, you're going to find a whole bunch of subdivisions. For example, this is the river. A braided stream, incidentally, is a stream that's got multiple channels that kind of wind around each other, like braiding your hair. Here, you're going to find that you have one bar that more or less is parallel to the flow of the stream. Compare that with this bar, which has flow that is 90 degrees to the direction of the stream, because what's happening is the water is wrapping around. What kind of paleocurrents are you going to get with this? And how are those paleocurrents going to change or vary from this? What do you get? Differences. Now, each one of these subdivisions are going to give you part of the overall picture for what the total braided stream depositional model is all about. All right? So, again, it's admission time. When we give you stuff in Geology 111, and to a lesser extent Geology 112, and we present it in this nice, easy, interpretable fashion, where we say quartz arenite sandstone equals beach, or breccia equals alluvial fan, that was the simplistic way of looking at things. In reality, those rocks can be deposited in a number of different environments, including here, where you can get a lot of breccias deposited in a braided stream, depending upon where it actually is. Okay? Rivers are not just channel and floodplain. Rivers have many, many, many subdivisions, which will independently leave evidence of their existence in the rock record. This is where we get into the idea of what sedimentary facies are. A sedimentary facies is a subdivision of an overall depositional model. And the best way of illustrating this, or to explain this, is to imagine all the subdivisions that you would get in an environment. Let's turn back to something we already know, okay? A beach. If you were to go to Dolphin Island, you would find the swash zone. You would find the dunes. As you got offshore, you would find the longshore bar. You'd find the longshore trough. You'd find some places where there's been a channel cut through the beach. Every one of those subdivisions will leave behind different evidence about what they were. And again, you can go down there now and look at them and you'll see them. You'll see that a channel is going to have an erosive bottom contact with sedimentary structures being deposited on top of it. That makes sense. You can see it happening. But in the rock record, that sequence of characteristics, you're going to have to interpret that as meaning it was a channel in the past. All right, you got it? Each one of those is a facies, a subdivision of the overall model. And that's why we are talking about them now. Now, don't let this in fact, I'm guilty of the very thing I said earlier about bad slides. We have a lot of writing and stuff on them. This is intentionally bad here. This is a diagram that is summarizing a vertical succession, sedimentary structures, and what it's got is all of the different information on here, summarizing everything. It allows you to look at different components and come up with what these different facies ultimately are about. And that's not a bad that's a bad diagram for seeing it because it's too detailed. How do you define sedimentary facies? This look familiar to you at all? This is why you're in the field. When you're in the field, you record as much information as you possibly can. And from that, you can identify and distinguish individual components that ultimately will lead you to a larger scale picture of what you're dealing with. So sedimentary facies are defined on the same things that we're going to be recording in the field. Now here's some things you need to worry about. Now what I'm going to start doing now is explain how you interpret things as well as some of the limitations to this. What I want you to consider now is a series of sedimentary rock units that you have identified in the field. This differs from this in what way? Two ways actually. Grain size is one of them. This is finer grain, and I'm trying to make that indicate that it's kind of like a shale or siltstone. This is a sand. This is a sand. How does the sand differ from that sand? Why does it deflect in this direction? It's coarser, and then notice it goes back to being finer again. What do you think this thing is identifying? What's that symbol reflect? Lamination. What do you think? Parallel lamination? How about this one? What's different about these two? All right, this is my symbol for low-angle cross-stratification. So in other words, what we've done is very simply cut this down. We have a siltstone, we have a parallel laminated fine sand, we have a low-angle cross-stratified coarser sand, and then we go back to this again. Now the thing to know about facies is that a facies is variable and can be reproduced. The idea is that each facies is dependent upon the conditions at the time. If sea level were to rise, for example, what you'd find is that the facies would move inshore or outshore, depending what they are. It's not unusual to see facies repeated again and again and again if the conditions returned the way it was before. Okay? So looking at a diagram like this, you can interpret depositional facies based upon criteria, which I haven't given you enough of this, but this bottom part here, let's call it offshore in water depth of maybe 10 meters, the shore face in water depth of maybe 5 meters, the swash zone, that low angle cross stratification is characteristic, it's right at 0 for sea level, and then we go back to shore face. So ultimately what we see here is an apparent sea level drop followed by a sea level rise. And while the first thing you're going to think of is you're dealing with a regression followed by transgression, think again, facies have a tendency of shifting back and forth. Sea level has not changed all that much in the last 20 years, but if you go to Dolphin Island now, you're going to see channels that are cut into Dolphin Island where there were no channels a few years ago. From your point of view, the bottom of the channel is going to indicate a sea level rise because there's water sitting on top of what was the swash zone. You understand how you've got to be careful how you interpret these things? There's one other thing you have to also be concerned about. Over time, you're recording not only transitions in terms of deposition, but you're also recording changes in potentially evolutionary developments. Case in point, consider the fossil content. These are supposed to be different fossils. Well, this is, I don't know, it's a fossil smiley face. Down here we find fossils of one type that are in these two environments. Now notice, there's the swash zone. The swash zone here has exactly the same sedimentary criteria as it does up there, but notice the fossils are different up here. It doesn't necessarily mean it's a different facies. It means that from the time this was deposited, these blue smiley faces kicked the bucket and were replaced by a related but different species. So in other words, no matter how much you want to stay away from paleontology, you have no choice to still remember that paleontology is recording things as well. And by the way, after a while you'll realize that certain fossils only occur in certain environments. The fossils themselves can tell you an awful lot about the nature of deposition that was going on in the past. Okay? But remember, be cautious. You also need to recognize that laterally you're going to be seeing some changes. And again, I ask you to think about Dolphin Island. If you start walking along Dolphin Island, along the swash zone, eventually you'll come to channels, the things that have been washed through by the last hurricane that came through. Those channels shift over time. And it's not unusual to see that laterally you're going to get some variation. Here's a classic example of a channel cutting across what had been different layers being deposited at different times. Okay, so you have to keep your eyes trained to make sure that you consider lateral changes as well. So when you're in the field, going out to an outcrop and measuring up is great, but every once in a while, put your hammer down, go back and look at it like this and see if there's any lateral changes you're going to get. And it's not a bad idea every once in a while too, if you have a really good outcrop, get your eye right down to the outcrop like this so you can actually see the contacts laterally, and you actually will be able to see if there's any inconsistencies in terms of horizontality as well. For those of you that are planning, anybody going to be here for geophysics in the fall? All right, if you're here for geophysics in the fall, I'll teach you the importance of actually looking at things sideways, because your eye can see an awful lot more if you're looking for parallels in that direction than if you're looking straight down on it. Yes, sir?
I need to find glass, the testing glass for test next door, and I think it's over here. I'm sorry, I'll be very quiet.
You mean for hardness stuff?
Yeah.
We're storing glass in here now, are we?
No, I think we left it here.
Okay. All right, well, have fun looking for it, okay? All right. I put this diagram in here again to explain that if you sit down and start thinking about all the different subdivisions you can have and try to put it onto a single graphic means of interpreting things, you're going to fail. This is where the cluttering comes into it. So this diagram is not meant for you to do anything except to look at it and go like, I'm glad I don't have to look at this. What you're looking at are all the different facies that have been interpreted based upon the combinations of things here. It's foolish to try and to do it in this fashion. What you have to do is look at the data you're getting and try to make interpretations on your own. Okay? Ultimately, we're going to be talking now about what's called facies modeling. The idea is you record all the information in the rocks. You sit down and try to identify which combination of criteria are important to determine which facies that reflects, and then you take the combinations of the facies and come up with a depositional environment. Now please note, as I said, facies are not necessarily unique to environments. Take, for example, a floodplain. A floodplain occurs when you have a flat area around a river that floods. A floodplain will be characterized probably by laminated, silty sediment with small current ripples in it. Probably rootless, because plants grow on the floodplain, right? Maybe you'll see the occasional dinosaur bone or bone of something that died on the floodplain. It's going to be a reddish colored shale because it's oxidizing. But if you were to look at a floodplain deposit for a meandering river, a braided river, and an anastomosing stream, and an alluvial fan, it would be identical in all of them because it's the same type of conditions. So you can't just simply look at a red shale and say it's a river. You understand? You've got to be able to look at the combinations of things. That's the facies modeling component. And when it comes to doing this, again, this is a cautionary note. I've seen this happen so many times where you'll have geologists that are in the field, and the field may incidentally be in a core lab, where you'll see these guys coming in and they'll pull out a core, and it's basically the same as a vertical transition of rocks. And they'll say, yep, river, 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 and they're out the door. Unwise. Because if you're going to do this right, what you need to do is take into account all of the information you see. Sometimes it actually takes a thin section where you look at the rocks to get an idea of what the interior components of the rocks are composed of. The best thing to do is to not think of interpreting the data when you're in the field. Observe, record, sample, come back and start thinking about it. Especially if you've got some beers. Now, I'm a firm believer that a little bit of relaxation is always good. I'm a firm believer that sleeping on things before you actually come up with interpreting them is also a good idea. When you guys are working professionally, don't be rushed into making decisions. Because I'll tell you right now, the people you work for will remember every mistake you made. They're not going to remember their successes. That's what they expect you to do. So be cautious without kind of, not giving the information they actually need, okay?
Career
Well, that's why I said take it home. Did I say take it? I did say take it to your office. Oh, okay. You're right. Bad, Doug. Take it to your home. Actually, I do some of my best thinking in the bathtub. Probably didn't need to tell you that either, did I? All right. And then you can interpret things. So going back to these diagrams I gave you for examples before. So here they are, the diagrams that are showing you different vertical transitions. But here you can see the interpretations of what the facies are. This first section here shows you a lower shore face, the middle shore face, the upper shore face. These are divisions based upon the nature of the sedimentary structures, the sand, grain size, etc. Then you get into the foreshore and backshore. It's what I call the swash zone. There's the dunes. When you look at the combination of these things, not only can you say it's a barrier island model, but it's a regressive or prograding model. The idea now is that this was a deposit that was being produced by some advance in the sediment or retreat in the water. It was building outwards. What a powerful resolution technique if what you're looking for is a thick, porous sand that contains oil. And by the way, if I'm not mistaken, this is one of Roger Walker's diagrams. He's an expert at the Cretaceous. This is the type of sediment that was filling in the Western Interior Seaway in the middle of the Jurassic and Cretaceous, where they're getting an awful lot of oil and natural gas out of the ground right now. All right, now that is this first lecture. And before, because I know that, didn't some people have to...